Hello everyone. Welcome to the course Experimentation with WLAN Toolbox of MathWorks. I'm Sheila CS, pursuing PhD under the supervision of Professor Joy Curie, Network Research Lab, Department of Electronic Systems Engineering, IISc Bangalore. This is a course for beginners to learn and explore the WLAN Toolbox of MathWorks. The course contains the conceptual study and discussion of simulation experiments that emerged during my research work on IEEE 802.11ax. The objective of this course is to help the students and research community, those who are new to the WLAN technology or WLAN toolbox. Before going to the experiments, I felt there is a need to understand more about the WLAN toolbox. So this is a video on introduction to WLAN toolbox. So without further delay, we will see what WLAN toolbox offers to researchers or designers. WLAN toolbox provides standard compliant functions for the design, simulation, analysis, and testing of WLAN communication systems. It includes configurable physical layer waveforms for the IEEE 802.11 family of standards. It also provides transmitter, channel modeling, and receiver operations, including channel coding, modulation, uh, special stream mapping, and MIMO receivers. The toolbox provides reference designs or examples. It helps you to perform baseband link level simulations and multi-node system level simulations. You can generate waveforms using waveform generator app. You can also study the effect of RF designs and interference on the system performance. As I told, you can use this propagation channel models in order to generate a channel model, and you can change its parameters. So to summarize, the WLAN toolbox enables a faster and most robust WLAN design. The designers and test engineers can use standard compliant functions for the design, simulation, analysis, and testing of wireless LAN communication systems. In fact, the WLAN market very much needed such a deployment, such a development and testing capability. Earlier, designers were spending precious time in creating reference models, generating test signals for their systems. Test engineers were also struggling to verify the performance of a newly designed WLAN product. Now, designers and test engineers can have a head start in their design efforts for a product and test their system. So, end-to-end simulation and algorithm development is possible. Measurement and analysis of the system performance is possible. The over-the-air waveform transmission and reception with software-defined radios and RF instruments can also be done using the WLAN toolbox. So now let's see what is the propagation channel model. So the propagation channel models are the channel models for 802.11an. It let us to model CISO and MIMO transmit receive links with IEEE standard defined channel models. So you can see here there is WLAN TGN channel model, TGAC, TGAX channel model, etc. So there are these are actually the system objects. So there are various system objects. What is a system object? A system object is a specialized MATLAB object. Many toolboxes like LTE toolbox or communication toolbox will have such system objects. System objects are designed to implement and simulate dynamic systems with inputs that change over time. We know that many signal processing, communication, and control systems are dynamic in nature. So in a dynamic system, what happens? The value of the output signal depend both on the current value, or the instantaneous values of the input signal, and also on the past behavior of the system. So the system objects captures this thing. So it has internal states to store the past behavior, and this is used to in the next computational step. So we will see what is WLAN TJX channel. So this filters the input signal through 802.11ax indoor MIMO channel. So it has various properties which can be changed according to our requirement. So you can see here there are various delay profile which is already provided by the toolbox. So based on your simulation, what you want to model, you can accordingly choose different channel models like A, B, C, D, E, or F. So model A is actually flat channel model. This is rarely used, but if you want to design indoor, see the performance of indoor residential scenario, you can go for channel model B. D is typical office enterprise. This is outdoor hotspot is channel model E. You can read more on this on the documents which is provided by IEEE. So if you compare, you can see the breakpoint distance is different for different channel models, and the breakpoint distance used by Toolbox is so it depends upon the propagation model. So here a D is the breakpoint distance here. Depends upon the path loss model which is being used. We'll see more on this in the upcoming videos. Then if you compare here, if you see the table, the delay spread also increases with say B has 15, E has 100, F has 150. So as the number of tabs increases, the delay spread increases. The channel is modeled as a filter. B is 9 tab filter. E is 18 tab filter. So the first two experiments, we spend more on time on this in order to understand what is the channel impulse response of various channel models, B, D, or E, and also we see what is the channel frequency response, and we will understand more in detail in the first two experiments of our study. So the channel bandwidth is one more property. Default it is 80 megahertz, and 11ax we know it supports up to 320 megahertz. So you can see all these, whatever the standard supports, it is there in the toolbox. The carrier frequency is again default is 5.25 gigahertz. You can change it and set it to 2.5 gigahertz as well. The environmental speed is 0.089 kilometers per hour. So this is the default. Typically, Wi-Fi is meant for static environment. But if you want to know, or if your application demands such that you need to know what is the performance when the speed increases, you can change this value to the higher value, say pedestrian or vehicular, and do the simulation. In that case, you need to enable high Doppler. So I'll explain that. But here you can increase the speed. So the transmit receive distance, again, whether it is you're in the LOS or NOLOS region, you can accordingly change this distance. As I told, the breakpoint distance for say model B is 5, for model D is 10. So if you want to simulate a scenario to capture NLOS FX, then you will have to set the distance greater than this breakpoint distance. Then the transmission direction to mention whether it is uplink or downlink. So default it is downlink, and the number of transmit antennas default it as 1. So it will have some default values. Each of these properties you can change it accordingly. So the distance between the transmit antennas, so it's 0.5. It's like say lambda by 2. So expressed in terms of wavelength. Then the number of receive antennas. Then the large scale effect. So if you want to model the large scale effects, such as path loss or shadowing, you need to enable this. Default, it will not consider any large scale effects, but if you want to include the large scale effects in your simulation, you may have to enable this. Then again, you can include the number of flows, the number of penetration walls, and also set the penetration loss of each wall. Default it as 5 dB. You can verify, you can modify this again. Then like this, you will have so many properties. For example, again here, if there is something called source of random stream, default is global, and otherwise it is MT19937AR with seed. Here you can give different seed values in order to realize a different channel. In the global stream, if you set it to global stream, if you use the recent function, then it will reset the filters and also creates a new channel realization. So I'll explain more on this when I do an experiment. We will see what it is in detail. So again, this path gains output, you will enable if you want to obtain the channel characteristics, etc. So if you go to a particular system objects, you will have many properties like this. You have to read more on this, understand, and set the values accordingly. Then next, we have one more configuration object, that is WLAN HE SU config. This is used to configure high efficiency single user data transmission or high efficiency extended range single user transmission. So as the name indicates, it is used for single user, that's like OFDM mode of transmission. So again, you have different channel bandwidth you can choose. Say 20 megahertz is a default. Again, if you want extended, if you have to go for ERSU or PPDU format, you may have to enable this extended range. Default, it is disabled. Again, if you want to use upper 106 tone, you'll have to enable this. Then the number of transmit antennas, again, spatial mapping, different kinds. Then if you are going for MIMO, you may have to use this. So based on the applications, you have different properties. Again, MCS, the modulation coding scheme, default it is 0. If you want to change it and set it to some value, say 5 or so, you can change it and set it. Again, DCM is false. So DCM is like dual carrier modulation. So for robust reception, DCM modulates the same information on a pair of subcarriers. This effectively halves the transmission rate compared to the non-DCM transmission. So default it is set to false. You can enable and see the effect. The channel coding type. So FEC coding is LTPC is a default. It also supports BCC. And we know that 11AX supports BCC and LTPC. So as I told you, WLAN Toolbox follows the standard, and whatever is specified by the standard, most of the properties are implemented, or most of the features are implemented in WLAN Toolbox. So this is a payload length in bytes. You can change it. Default is 100 bytes. Again, the guard interval 11AX supports 3 types of guard interval. So 0.8, 1.6 or 3.2 microseconds. HLTF type is again 3 types, 1x, 2x, and 4x. 11AX supports all these 3. And you can set BSS coloring, spatial reviewers. Again, the mid-amble periodicity. Say, I told you, like if you want to simulate the high speed, I mean mobility, you have to take, if you want to take into consideration in your simulation, then you have to say you increase the environmental speed. Then what happens? Channel, you can use this mid-ambles for channel estimation. This is because the HE5 of 11AX supports mid-ambles. So mid-ambles facilitate updating the channel estimate during HEPPDU reception. So mid-ambles are also useful in high mobility scenarios, and due to the variation, significant variation in the wireless channel over the duration of PPDU, there you can set the periodicity. More is the periodicity, better is the accuracy of the channel estimation. So like this, this is HESU. So we will see what is it actually. Say for example, this is object WLAN HESU config. I have created a single user high efficiency configuration object. So let me evaluate this. So now if you see, so whatever the parameters or properties I discussed, it is there. Extended range is 0, bandwidth is default, and the number of antennas, transmit antennas, antenna is all default. It's a CISO. Then MCS default value is 0. The channel coding is LDPC. The data length is 100 bytes. The guard interval, HLTF type, all is set to the default values. So now if you want to change this, say for example, I want to change the MCS. So now what you should do is, CFGSU is a variable wherein you have stored this system object. So simply take that and put .mcs extension and set it to say 5. So now if you see, the MCS is set to 5. So if you want to change the length, our default it is 100 bytes. So now if you want to change the length to 500 bytes, again simply change that particular property to 500. So now it is set to 500 bytes. MCS is set to 5. The data length is also set to, payload length is set to 500 bytes. So like this, you can change any of the properties. And there is one more command called ruinfo. So ruinfo of CSGSU, if you do, it gives resource in RU unit, that's resource unit information. So it was HESU configuration object, meaning you have single user. So number of users is one, the number of RUs is one. It means entire 20 megahertz bandwidth is given to a single user. RU size is 242. See, we know that in 11AX, like 20 megahertz bandwidth has 256 tones or 256 subcarriers, but out of which only 242 are actively used. They are called as active subcarriers. The remaining 14 subcarriers are unused. They are used as like guard band subcarriers and the null subcarriers. So 6 at the left and 5 at the right, and in between 3 subcarriers are unused. So you have 242 active subcarriers. So RU size is 242. You have only one RU which is having 242 tones. So the number of space-time streams per RU is also 1. RU number is 1. So using this command RU info, you can obtain the RU allocation information. Now let's see how to model multiple users. We know 11AX for the first time supports OFDMA mode of transmission, and we will see how that can be modeled using WLAN Toolbox. So this WLAN HEMU configures HE multi-user transmission. HE refers to high efficiency, that is 11AX multi-user transmission. So for this, input is allocation index. So there is something called allocation index. Based on the allocation index, users are allotted different RUs. So what is RU? RU is a resource unit. The entire bandwidth is divided into group of subcarriers, and each group of subcarriers is called as resource unit, and one particular resource unit is given to one particular user. So this is again standard specified. 11AX standard amendment specifies this. So there are different allocation indexes starting from 0 to I think it's up to 242. So based on these allocation index, different users are assigned to different RU. For example, allocation index 0, 20 megahertz channel is divided into 9 equally sized resource units, and the RU size is 26 tones. Then if you go for RU 16, say 0 to 15, it is OFDMA configuration. If you see here, what is the change? These two are clubbed to form one resource unit. So this 52 tones is given to one single user. Remaining 7 RUs are given to 7 other users. So like this, there are different combinations which is already specified by the standard. If you go for RU 16, RU allocation index 16, the first 52 tones is given to one user. Next 52 tones is given to the other user. Then 106 tones is given to one user. If you go for 17, what happens? So this is 15 plus number of users. If it is 16, this is shared by only one user. If it is 17, this will be shared by two users. So sometimes you may not be able to understand in the first read, you may not get what's actually the allocation happening. So this can also be verified and understood better using WLAN Toolbox. That we will see when you go for HEMU. So before understanding that, we will create HEMU configuration, say with the RU allocation index 0. So again, similar to HESU, again you have different properties where you can set. So the number of transmit antennas 1, the guard interval, all these takes default values. So bandwidth is 20 megahertz, allocation index is 0. So if you use RU info of the CFG-MU, sorry, it is CFG-HEMU. So you can see there are 9 RUs, and size of each RU is 26 tone. They're equal sized RUs. RU indices is like 1 to 9. The number of RUs is 9. Number of users are 9. So each user you have one space-time stream. So now let's change this RU allocation index to 16. Then I'll see what is the RU allocation information. So as I told you, what was it? First 52 tones was first 52 tones. So for 16 RU allocation index, 52 tones, next 52 tones for the second user. Then 106 tones is given to the third user. So first user, second user, 106 tone is given to the third user. If you change this to 17, what does it change? Number of RUs is still 3, but the number of users are 4. It means the 106 tones is shared by 2 users. So the number of users per RU in this third RU is 2. The number of space-time streams per RU is again 2. So this is a change. So in earlier case, what was happening? There were number of RUs were 3, number of users were 3. The 106 tone, only one user were given, only one space-time stream. Here, when you change it to 17, still RUs are same, 3, but the number of users are 4. The 106 tones is shared by 2 users. So the number of space-time streams is 2. So like this, HEMU, when you use this configuration object, you can give the allocation index, which is defined by the standard. And more, if you want to read more on the allocation index, again, there is a documentation provided and you can refer to this. Then you can also show this, whatever we have seen, you can plot it and then pictorially and see using a show allocation command. So if I type show allocation CFG HEMU, so it will show the RU1 is used by user 1, RU2 is used by user 2, RU3 is used by 2 users. It is shared by 2 users, 3 and 4. So after this, we'll see one more function which is very important and it is frequently used when you code. That is, we will see first WLAN waveform generator and also this indices. So once you generate the configuration object, you can use this WLAN field indices and give the configuration object as an input parameter to get indices of different fields of the packet or the frame which is being generated. When you go for multi-user thing, it is called as multi-user frame. So now here it is CFG SU, that is HESU. So using this int, I can get the index points for the different fields of the packet preamble. For the different fields of the packet. So first, if you see 1 to 160 samples corresponds to LSTF, then 161 to 320 samples corresponds to LLTF. So like this, you can obtain the different index points for the different fields of the packet. So LSTF, LLTF, and LSIG, that is a long legacy short training field, the legacy long training field, and legacy signaling field. These three are called as legacy part of the packet preamble. So here the bandwidth uses 20 megahertz. The sampling frequency is 20 megahertz. The sampling interval is 1 over 20, that is 0.05 microsecond. So this is LSTF is 160 samples. So when you know the number of samples and the sampling interval, you can compute what is the duration of that particular field. For example, LSTF has 160 samples. Multiply 160 by 0.05 microseconds, you get 8 microseconds. So 8 microsecond is the length of LSTF, and that is standard specified. Similarly, LLTF also has 160 samples in it. So the length of LLTF is 8 microseconds. But if you see, LSIG has 80 samples. So the length of LSIG is 18 to 0.05 microseconds, that is 4 microseconds. So what is the length of the legacy part of the packet preamble? It is 8 plus 8 plus 4, 20 microseconds. So all these is like standard specified. If you see, refer to any document of the PPTU format, you can see the length of different parts of the packet. So if you refer, you can see that the legacy part of the packet preamble occupies 20 microseconds. So this in or WLAN field indices, I mean, it is very much useful. So for example, here only I have used, so before that, there is something called WLAN waveform generator. What is this? So you are generating the waveform, giving in the bits. So PSDU is, you are creating a PSDU. This randi01 generates a random 01 bit pattern. You're specifying what is the size of the PSDU. Then this has random bit pattern in it. CFGSU is the configuration object. So TX waveform is the waveform for this particular uh, randomly generated data bits. So if you want to read more on that, you can open this function. So this is a waveform generation. It accepts the data bits configuration format and generates a waveform for the given configuration format and the information bits. So this waveform consists of a single packet with no ideal time, but you can also mention what's the ideal time between the packets. For OFDM formats, okay, what is this data scrambler? So we know in a OFDM transmission, the data bits are initially scrambled. Then you do forward error coding like LDPC or PCC encoding on that. Then this bits is mapped into complex constellation symbols using the constellation mapper. Then these complex constellation symbols on this, you apply IDFT. It's passed through IDFT block in order to obtain complex waveform. So all this is done internally by the WLAN waveform generator. Simply giving data bits at the output of the transmit waveform, there's nothing but the complex NS by NT waveform, where you do data scrambling, encoding is done, constellation mapping is done, and IDFT is also done. So this TX waveform is a output complex NS by NT waveform. What is the NS? NS is the number of samples, and NT is the number of transmit antennas. So here default NT is 1, like CISO configuration. So here if you see, this TX waveform is a vector. 3600 samples it has. And what is the duration of this TX waveform? Simple. Since it has 3600 samples, simply multiply it by the sampling interval. 3600 into 0.05 microseconds gives the length of the transmit waveform. So now I have already generated the TX waveform. Making use of this indices, what I'm doing, I'm here extracting the HELTF portion of the transmit waveform. So this in dot HELTF1 colon like this, if you give, it means it is just extracting the HELTF portion. So HELTF portion, if you see in int, it was occupying from 721 samples to 1040 sample was corresponding to HELTF. So the complete thing, the transmit waveform, this now HELTF transmitted has that portion in it. So for example, I can give you one simple example. Say at the receiver end, you do this. Same thing can be done at the receiver. You have, say, received waveform. Using this field indices, you can obtain index for different fields of the received waveform. You can extract the HELTF portion of the received waveform. Since you know what is a transmitted HELTF, basically HELTF is used for channel estimation in 11AX. So they're the pilot symbols which is known. So using those known transmit HELTF symbols, and you have at the receiver the received HELTF symbols, you can do channel estimation. So this is one such simple example of using WLAN field indices. Then we discussed what is TJX channel. So in TJX channel, yeah, this is I told you, like you can set the different distance, you can enable path loss, and path GAN's output is set to true, where we can, in order to obtain channel simplest response. We will study this in detail in the upcoming videos. So delay profile here, it is set to model D. There is one more function where you can obtain the information on TJX, that is like using the info of TJX. So it tells like what is the channel filter coefficient, what is the number of taps in a channel, what is the path loss associated with it. Everything can be obtained using this function info of TJX. Then after this, I would like to discuss one more function, which is WLAN HEOFDM info of. So this basically gives the OFDM information for HE transmission. Here you need to specify the field. You say I want to know more on HELTF field. Then you should also mention the configuration object, CFGSU. We have CFGSU already created earlier. Yeah, CFGSU. So if I do this, yeah, see, if you do this, the HLTF part, F50 length used for this is 256. The CP length is 64. The number of subchannels is 1. The number of active tones is 242. As I told you, it is HE single user. A single user occupies a complete bandwidth. 20 megahertz bandwidth, that's 256 subcarriers. Number of active subcarriers are 242. Here, it also tells what are the active frequency indices. So in this 256 subcarriers, which particular subcarrier or the tones is being used. Okay, and then it also tell which are the data subcarriers in that. 234 are the data subcarriers, and there are 8 pilot subcarriers. You can obtain those subcarriers, like which subcarriers corresponds to pilot subcarriers. So now this information is stored in answer. Okay, so let me write answer dot pilot indices. So these are 8 tones which corresponds to pilot subcarriers in 242 active subcarriers. Then you can type obtain what are the data indices. So data indices. So okay, let me store this in a variable. Then try to obtain the data indices. Because the answer was overwritten in the previous case, that's why I guess there was some error. Yeah, so better to store in a particular variable so that it is easy for access. Earlier I forgotten to store it, so I tried to access using answer, but that was overwritten and hence it was showing up some error. Okay, so now you have 234 data carriers, and which tones correspond to data subcarriers is there. So like this, you can also obtain what is the active indices. How many active indices we have? We have 242. So this can also be obtained. The variable is info1. So here this has 42 active subcarriers, which can be obtained. So this can be used. Why I'm telling all this is maybe if you know this when you write a code, this information would be required at some point. You may access this in order to do something else. So like this, many functions are available. We will explore more on this. So whatever today I discussed, these are some of the basic things which is present or you should know before starting our experiments. But when I do a particular experiment, I'll tell more. I may make use of other system objects in the code, or I may come across some other functions which are something like this very helpful in order to understand some of the internal things. So those things I'll explain whenever I go to the particular experiment. Hopefully, I hope this particular course help all the beginners who want to learn more on WLAN Toolbox or explore more on WLAN technology. Thank you for watching. So I have some set of experiments which is being planned. Initial few experiments will be simple to understand, and then the complexity grows as I proceed with the number of experiments. The objective, as I told you earlier, it is to help the students or researchers or designers so that they get introduced, so that they get used to this WLAN toolbox and use this toolbox in order to carry out their own research work. Thank you. Now I'll stop the recording. Thank you all.